do f omega plus 1 of 3. Well, we can go back to our rules. This is the exact same as the thing before it ever. So we can take 3 copies of the f function, the one that's minus 1 from this. So we have 3 copies of the f omega function. So let's write that down. F omega of f omega of f omega of 3. And we know that this is going to be f of 3, which is already a pretty big number. But now watch what happens. We take this huge number now, and we're going to plug this into the omega slot, which is going to be a huge number. Like this is going to replace this whole thing here. And then we take that huge number and plug that into this slot. So now you can see where the power of this is coming from. This is a recursive application of huge numbers into the subscript slot. So that's pretty cool. And we can keep on going with this. Oh yeah, I'm going to go over something, one more thing too. The reason why you can't just plug this 3 into the omega and get like 3 plus 1 is well, first of all, it makes just a small number, and that's boring. We want to make large numbers. We don't want to make small numbers. But you can kind of think of it as you need to get rid of this number first before you can attack this ordinal with the 3. So it's almost like you have to expose this ordinal before you can work on it with this. So you have to follow the rules. You have to minus 1 here, get rid of all this stuff here, and then you can finally diagonalize, basically. So we're going to go through a couple more examples of arithmetic and how you break apart infinite ordinals. But not correct. All right, so there's nothing stopping us from going further. We can do f of omega plus 2 of 3. And same thing, we do 3 copies of the previous function. So we're going to have f omega plus 1 of f omega plus 1 of f omega plus 1 of 3. And we know how to evaluate this function because we've done it right here. So this is going to be a huge, huge number. This is going to break this apart into this many f omega functions, and that's going to go recursively through the whole thing. So even adding 1 to this really blows this function completely up. And we can keep going from there. We can have omega plus 3, omega plus 4, omega plus 5, and we can even have omega plus omega, which turns into omega 2. So with a fresh board, I'm going to do an example of that. So we're going to plug omega 2 into the fast-growing hierarchy and see how we would evaluate something like that. All right. F omega 2 of 3. Now once again, we can't attack this omega with the 3 right away and turn this into 3 and do 3 times 2 is 6. That's silly. We want to expose this omega. There's a 2 in front of it right now, so we have to break this apart. And how we break that apart is we take omega times 2 and we turn it into omega plus omega. So f omega plus omega of 3. Now we have an exposed omega that we can diagonalize. So this is going to equal f omega plus 3 of 3. And we know what to do from here. We can iterate this down and make copies of it and go from there. That's something we've done before. Okay, so we have omega 2. Well, why not omega 3? Omega 4, omega 5. And we can even do omega times omega, which turns into omega squared. So let's do an example of that. F of omega squared of 3. Once again, this 2's in the way. We got to do something. So we're going to break this apart once again into its constituent parts, whatever. Omega times omega. So let's do that. F omega times omega of 3. And finally, we have an omega that's exposed here. Turn this into a 3. F omega times 3. Okay, well, wait a minute. We're still not done here. We have to do some more work. We have omega 3. This 3 is in the way. So what if we keep 2 of the omegas and then add another omega? So we have omega times 2 plus omega. That's still omega times 3. So let's do that. F omega 2 plus omega of 3, which is going to equal F omega 2 plus 3. And that we can finally evaluate because we have a number here which we can iterate down and plop into the fast-growing hierarchy or whatever. So we can do recursive thing. And we can keep going from there. There's really no end. We can go omega cubed, omega to the fourth, omega to the fifth, and we can even do omega to the power of omega. Okay, well, this one is a little bit different, so we're going to do another example. Placement. Okay. How would we evaluate f omega to the omega of 3? Now this one is a little bit different because now the omega is in the exponent part, but we're still able to diagonalize. So that rule of this being the omega is kind of touching the number here and it's able to diagonalize, it still kind of applies. So we're able to take this 3 and diagonalize it and turn this into a 3 here. So this is going to equal f omega cubed of 3. Alright, so what do we do there? This 3 is in the way now, so we have to start breaking this apart. So what if we take omega squared and we go times omega? This is still going to be omega cubed. So let's do that. F omega squared times omega of 3. Now we have an exposed omega, we can turn this into 3. So this turns into f omega squared times 3 of 3. This 3 is in the way now. So what if we take 2 copies of omega squared and then leave one out? So we're going to go f omega squared times 2 plus omega squared. Then we can break this apart again to omega times omega. Writing, sorry. Omega times omega of 3. This omega turns into a 3. Now this is in the way, so let's break this into omega times 2 plus omega. Let's do that. Plus omega. And finally we have this final one which we can turn into a 3. And we have a number finally that's not infinite ordinal, and we can start doing our recursion thing with our fast-growing hierarchy. So finally we get something we can work with. So this comes from this. So as you go on, it becomes a little bit more work to do the arithmetic, to break this apart into something that you can use, but it's all just mathematics that you're already familiar with, laws of exponents and like multiplication and stuff like that. But just remember that you always have to break this down into addition. So you go from exponentiation, you break this down into multiplication, and then finally into addition, into a number that you can finally use. So it's like you're whittling down the number to be able to use it, type of thing. Okay. But it doesn't end there. Of course not. We can have... Alright, so we just had an example of omega to the omega. What about omega to the omega to the omega? That's allowed. It'd be the same thing. Plug this into the fast-growing hierarchy, turn this into a 3. The whittling down process would be a lot more more intricate. You'd have to do some things with lots of exponents and stuff like that, but it's still doable. You could do omega to the omega to the omega to the omega. And you can keep going like this. Well, what's the limit of this? Where you can't do this anymore is a very important number, a very important infinite ordinal, and this is the infinite tower of omegas. And this is denoted as epsilon naught. And epsilon naught is a very, very important one because it's our first fixed point of the infinite ordinals. And what I mean by fixed point is it satisfies a certain equation, and that equation is this. Omega to the a is equal to a. And we can see this because imagine if we took omega to the epsilon naught. Well, what is that? It's an omega with an infinite stack of omegas on top of it. So imagine if we had an infinite stack of omegas and we kind of just plop another omega in there. Well, what is that? It's still just an infinite stack of omegas. Nothing has changed. So this is equal to epsilon naught. So that is what's known as a fixed point. And we can plug this, again, into the fast-growing hierarchy. But the difference is when we diagonalize something like this, it's a little bit different of a process. F epsilon naught of 3, what would that be? Well, instead of changing this into a 3 or things that we did before with omegas, this number represents the number of omegas in the tower. And for technical reasons, it's actually not exactly. It's one minus the number in the tower. So let's say if we had F epsilon naught of n, you'd get a tower of omegas that's n minus 1. And I'll go through later on why that is. I need the Veblen function to be able to show that, and that's beyond us right now. So we'll get into that a little bit later. But for now, just know that epsilon naught, whatever number you have here, you're going to build a tower of omegas that's 1 minus this. So for instance, we'll do F epsilon naught of 3. F epsilon naught of 3 is going to equal a tower of omegas 3 minus 1, so too high. Okay, well, that's kind of strange because that's not much bigger than we had before. I mean, this is the exact thing that I showed you before with just the omega to the omega. This turns into a 3, and that expands into that thing I showed you before. So how is epsilon naught any bigger than that? Well, like before, we can simply add 1 to this. Remember, any infinite ordinal, you can always add 1. So what happens if we take F epsilon naught plus 1? Well, we can do the usual thing and make 3 copies of this minus 1 function. So 3 copies of the F epsilon naught function. This here, we know is going to be omega to the omega, which is going to turn into omega to the 3. So this already is going to be a huge number. But now, we plug this into here. So what does that do? Well, this makes a tower of omegas in the F function that's this high. So this huge number that's way bigger than Graham's number or anything we talked about, we're going to plug that into the number of omegas in the tower. So that is huge. And if you can imagine this huge tower of omegas, and you put a 3 at the very top and whittle that whole thing down, the function itself would be bigger than the universe before you even began to stick it into the fast-growing hierarchy and make the number itself. So truly large numbers. And then you take that one and plug it into this slot, whatever. So the power of this really comes from when you go beyond and add other things to it or whatever. The recursion causes it really to explode. It's crazy stuff. And I think I'm going to leave it at that after, and we're going to go into the epsilon.